Hi everyone, and welcome back to the second video of this series. So a quick recap from the last video. So in the previous video, we talked about the ability to be able to address individual levels. So the first thing which we talked about was the need to address the level 0 and 1 in a qubit without exciting the other energy levels in our qubit. So we don't want any unwanted transition. We don't want any undesirable transitions. And so this is not possible with conventional inductances. So for instance, if we have an LC circuit, so uh, with a linear inductance, we only get equidistant spaced energy levels. So what we need is a non-linear inductive element. And I finished my video by stating that we will use some circuit elements, a particular circuit element which is known as a Josephson junction, which provides a non-linear inductance. So in this video, I'm going to talk about Josephson junctions, but first we have to be aware of how they work. So we need some background. So I'm going to introduce some background of the Josephson junction in this video, and I'll divide the whole um, approach into perhaps 4 or 5 videos so that it is easier for you to follow. So let's get started. Now I'm going to introduce a few things about superconductivity. And a good reference in this regard is chapter 21 of volume 3 of Feynman's lectures on physics. So I'm going to include it in the description of this video as well, so you may want to check it out. So to begin with, I'm going to mention this paper by 3 people, a paper from 1957. Again, I'll mention it in the description. Now, these three scientists, they gave what is known a very popular theory in physics, and it is known as the BCS theory of superconductivity. And they published this remarkable paper in 1957. So, just to summarize, key thing about superconductivity is that at low temperatures, they noticed that metals and in fact several materials which show some resistance to electric current below a certain threshold temperature, they show zero resistance to the flow of current. Also, another observation which they made is that below that certain temperature, there is an attractive force between electrons, and electrons actually don't flow independently, and they form pairs. They flow in pairs. So they call these pairs as Cooper pairs. And moreover, one of the remarkable thing was these Cooper pairs move in the same quantum state. And what this also implies is that it can actually describe the simultaneous state of a large number of electrons. So in this context, I'm going to talk about something known as the probability current. So I'm going to start with the Schrodinger equation. What I'm going to do next is I'm going to multiply this equation. I'm going to actually pre-multiply this equation with the complex conjugate of psi. And I'm also going to consider the complex conjugate of this equation here. And I'm going to write it as, and I'm going to subtract uh, this equation from this one. And what we are going to get is Next, what I'm going to do is get the right hand side of this equation. I'm going to substitute the expression for the Hamiltonian right here. And if you look carefully, the term corresponding to the potential, it will just cancel. And what will remain is only the terms corresponding to this. And if you look carefully, we can actually write this as, now I'm going to rearrange it. And if you consider this term from the property of derivatives, I can actually rewrite this in terms of the del operator. It can be shifted outside, and I can write this as this. Now we shall call uh, this term psi star times psi as rho. So in a macroscopic sense, you can think of it as it describes the density of Cooper pairs inside inside the superconductor. And so del rho by del T, this is the rate of change of the density of Cooper pairs at a point in space. And we are going to call uh, this quantity, which I've just written here. I'm going to call this as the probability current. Notice that there is no del operator here. So I want you to take note of that. And with this little kind of trick, as you might say, we can rewrite this equation here. We can rewrite it as follows. And this is a very well-known equation. You might even recognize it from classical physics. This is actually the continuity equation. And what this physically means is it describes the change of density at one point in time in terms of the divergence of a vector quantity. So this is actually the divergence of the J vector, and this is the J vector is actually the probability current. Now, from quantum mechanics, I want you to recall that uh, the expression of the momentum operator. So the momentum operator, sorry, and so the probability current, it can be rewritten in terms of the momentum operator, and I'm going to do just that. Now I'm going to manipulate this expression a little bit for our convenience. So I want you to note that this can be written as, now consider the complex conjugate of h bar over I psi star times del psi by del x. Now the complex conjugate of this quantity is this, which means that if you look at this expression carefully, I can write the probability current as uh, the real part of some quantity, and that quantity is psi star times b times psi. Now I can relate this to the momentum operator. So how does the momentum operator come into picture when we are talking about current? So this can be thought of as a charge moving with a certain velocity. Uh, that's how the momentum operator actually appears in this expression. Now, all this discussion until now was in the absence of an electromagnetic field. In the next video, I'm going to introduce an electromagnetic field and we'll see what will happen to the system. See you guys in the next video.